Okay, so in my last video, we talked about strong bases, and in the one previous, we talked about strong acids, and we learned how to calculate pH for both. We learned that using the equilibrium for the autoionization of water, that we can determine either the hydrogen or the hydroxide ion concentration as long as we can figure out at least one of them. Okay? And so we're going to continue to apply that concept, but now we need to look at weak acids and weak bases. So the big difference is that weak acids and weak bases do not ionize completely. So where strong acids and strong bases will completely give up all of their hydrogen or hydroxide ions, weak acids will only give up some of them. Okay? And so we have to determine, well, what exactly or how much of those ions are they going to give up in solution, and what does that do to the pH? So let's take a look at an example of a weak acid. Remember in the previous video I gave you the 6 strong acids and the 6 strong bases. Anything else is going to be considered a weak acid or a weak base. Okay? So here's an example, HClO, that is hypochlorous acid. It's a weak acid. And we could write this as reacting with water and forming hydronium, or we could simply write this as the ionization of the acid to H plus and ClO minus. Either way, they're essentially equivalent. Okay? And this particular acid has a Ka of 2.9 times 10 to the minus 8. Recognize that is a very, very small Ka value. Okay? There is a very limited amount of hydrogen ion that's going to be produced in this reaction. And we could write an equilibrium expression to represent that Ka value, the hydrogen ion concentration, times the concentration of the hypochlorite times the concentration, or sorry, divided by the concentration of the hypochlorous acid. Okay. So in this case, right, we can't make the assumption, because it's not a strong acid, that this is going to ionize completely, and so the concentration of the HClO is going to be much, much different from the concentration of the hydrogen in solution. So for this, we're going to use the same tool that we've used for other equilibria, and that is an ice table. Okay, so let's take a look at the ice table. And let's say that we're starting with a hypochlorous acid concentration of 0.1 molar. Okay? So we've got a initial concentration for the acid of 0.1. We have none of the hydrogen ion, none of the hypochlorite ion yet. Recognize that in the reaction it's all a 1-to-1 ratio. So for whatever amount the concentration of hypochlorous acid decreases, we'll call that X. It goes down by X, right? And the hydrogen and the hypochlorite increase by X. So we've got, for our change line there, minus X and then plus X and plus X for the two ions formed. Okay? We add those lines together to find the equilibrium concentrations, or to be able to solve for the equilibrium concentrations. Okay? And so we set up an equilibrium expression that looks like this. Okay? Now, some of you may recognize that what we're going to end up with, if we follow this equation to its logical conclusion, is a quadratic. Right? We've got x squared there on top. And we went through and did one of these before. We talked about acids and bases, just looking at equilibria, where we had to use the quadratic equation to solve for x. Okay? But we also did an example where we were able to make an assumption. So we're going to talk about that now, because it's an assumption we make with a lot of weak acids. Recognize that Ka is a very, very small value. It's a lot less than 1. And so the concentration of both the hydrogen ion and the chlorite ion, hypochlorite ion, are going to be very, very low. Okay? So low, in fact, that, well, so X is very, very small, and so that 0.1 minus X is really pretty much equal to 0.1. Okay? In other words, we're not going to produce enough hydrogen ion or hypochlorite ion to affect the initial concentration of the hypochlorous acid. Okay? So making that assumption makes our equation a whole lot easier, right? We can get rid of that minus X part. Let me shut this up because I don't know how far down this goes. Okay, we can get rid of that minus x component, and it just becomes x squared over 0.1 is equal to 2.9 times 10 to the minus 8, the Ka value there. Okay. So if we solve that equation for x, whoops, we get 5.39 to the negative fifth. Recognize that x is the concentration of the hydrogen ion. So if we wanted to calculate the pH, all we need to do is take the negative log of that value. Okay, so negative log of 5.39 times 10 to the minus 5, we get a pH of 4.26. Okay. Now, does our assumption hold? Okay, to figure that out, remember we need to be less than 5% ionized. Okay, so if you take the concentration of the hydrogen ion and divide it by the initial concentration of the acid, multiplied by 100, and you get 0.05% ionization, we're well within the realm of being able to make the assumption that the initial concentration of the acid is not changing. Okay, so let's talk about a weak base then. Process looks very similar when talking about a weak base. Okay, the big difference, of course, that weak bases also not going to ionize completely, but they are proton acceptors or hydrogen ion acceptors. Okay, so let's look at an example. We've got a weak base here, NH3, ammonia, reacting with water to form NH4 plus OH minus. Recognize in this type of equation, there's really no way to get around showing the water because the hydrogen has to come from somewhere. So in this case, water is serving as our acid. Remember, water is an amphoteric compound. Depending on the conditions, it can be both an acid and a base. And again, we can write an equilibrium expression for this reaction. The concentration of NH4 times the concentration of OH minus divided by the concentration of the NH3 is equal to Kb. And in this case, Kb is 1.76 times 10 to the negative fifth. So remember again, this is a weak base, and we know that by looking at the Kb. Kb is a very, very small number. Okay, there's going to be very limited ionization for this ammonia when it reacts with water. Okay. And so again, just like we did before, we're going to set up an ice table. We'll go ahead and use the same initial concentration. The problem will generally give you the initial concentration, or at least some way to solve for it. So let's say that we have a 0.1 molar solution of NH3. And again, it's all a 1-to-1 ratio, so our change line becomes minus x plus x plus x. Recognize that water is not part of the equilibrium equation, right? We don't include pure liquids. And so we get to leave that off the ice table completely. If we add those two lines together, we get 0.1 minus x, x and x, and so we plug that into our equilibrium expression and we end up with this. X squared divided by 0.1 minus x is equal to 1.76 times 10 to the minus 5. Okay? And again, recognize that we're going to end up with a quadratic. We don't want a quadratic. It's difficult to solve, it takes a lot of time, and the reality is this is not going to ionize to a very significant extent. Okay? Again, Kb is much, much less than 1, and so 0.1 minus x is really essentially equal to 0.1. Okay? That's the assumption that we're going to make. And so that makes our equilibrium expression look a little more like this. We've got x squared over 0.1 equals 1.76 times 10 to the negative fifth. Okay. If you solve for x, you get 1.3 times 10 to the negative third. Recognize that x is the concentration of the hydroxide ion. So if we take the negative log of that x value, what we get is the POH. Okay? pOH is negative log of 1.33 times 10 to the negative third is 2.88. And so to determine the pH, we subtract the pOH from 14. Remember that pH plus pOH always equals 14 for a dilute aqueous solution. And so what we get then is a pH of 11.12. Okay. And again, we could check to make sure that our assumption is correct. So we would take our x value, 1.33 times 10 to the negative third, and divide that by the initial concentration, which was 0.1, and we get something like a 1.3% ionization. So a little bit stronger of a base than what our previous acid was. We get a higher percent ionization, but still less than 5%. It's still a good assumption. Okay. Couple practice problems that I'd like you to take a look at in the text. Again, we're in chapter 16, numbers 65, 67, 69, 89, 91, and 93. The first three deal with acids, the last three deal with bases. Okay. There are a few more topics in this chapter. I don't think I'm going to cover them. It talks a little bit about polyprotic acids, that is, acids that contain more than one hydrogen ion. And you may have noticed when you looked at the table in the back for Ka values, if you didn't know, there's a table in the back with Ka values, that if you have a polyprotic acid, there are multiple Ka values. That's one for each hydrogen coming off. Okay. There are some equations that we could do there, but I'm inclined to leave that for your analytical series when you get to college. It also talks about the acidic effects of ions. Okay, so if you have an anion or potentially a cation with hydrogen in solution, you have the potential to either take a hydrogen from water or donate a hydrogen to an aqueous solution. And so there are some acidic and basic effects of ions themselves. So yes, you can affect the pH of a solution by adding a salt to it. I don't know, I'll have to think about that. I've not covered those in the past, but given the amount of time that we have and the amount of time we're going to need to spend online, I might consider it. But at the very least, we are going to talk about buffers here shortly, okay, which brings us into chapter 17. Chapter 17 also talks about limited, so before what we referred to as insoluble ionic compounds. If you remember, we did a problem just before we left with silver chloride, talking about, yes, it's insoluble or largely insoluble, but that doesn't necessarily mean there aren't ions in solution. So we may talk about that topic. It's pretty short too. So, and then we've got electrochem, and that'll pretty much get us through. So keep plugging away. It is important that you're able to view these videos. I guess technically I can't require this information, but as far as I understand it, the university is still online. So we're in a bit of a unique situation in that regard, even from the rest of the people at school, because we're actually a different institution technically. So. So if you are having trouble viewing these, we really need to get that figured out. I'm kind of curious to know if folks with Macs are the ones having issues viewing these videos, because I am creating them on a PC, so maybe that's the problem. In which case, for my Mac users, you may have to try and find a patch or something. I know when I watch these videos, it pops up as a VLC. I'm not a tech guy. I guess I don't really know what that means, but my guess is that somewhere there's a patch for Apple that would make that work. So, yeah, in order to make sure that you're still getting credit for the course, guys, I really do need you to be keeping up with the work, so that when we come back, all we'll have to do is some labs and a final exam. That's kind of what I'm shooting for at this point. I probably won't post anything next week because of spring break. But I'll try and get a few more things up here this week, and then the week after spring break, and hopefully that'll be enough time to finish covering all of the content. We can get back to labs when we return, and the final exam, and probably a test over equilibrium as well. So I haven't quite decided or figured out how we're going to do that yet. But all right, like I said, keep plugging away, and we'll get through it. So, take care, guys. If you need anything, please let me know.